Hi again, everyone. We are on to 2.5. It's continuity. So we had kind of a break with 2.4, but now we're back to the main stream of the conversation. This will continue with the ideas that we developed in 2.2 and 2.3. So what is this all about? So continuity, this is a key concept in the development of calculus, and eventually at the end of this chapter 2 we're going to define and see what the derivative is all about. If you remember that from the what is calculus video, that's where it's leading. So we need this idea of continuity to help us get there. Okay, so what's this all about? Here's the definition. We're going to say a function is continuous at an x value. F of x is continuous at x equals a if the limit of f of x as x approaches a is equal to f of a. So we're saying the limit of the function as x approaches a is equal to the function value at a. Okay, and we certainly know with limits that doesn't have to be the case, but here it's like we actually arrived at a itself, and these two things are equal. So we're just going to kind of describe what this is in a picture, and more importantly, what it's not. So we're going to see a few examples of things not being continuous, and then finally we'll see what continuous looks like. So let's begin with just a few drawings here. So I'm going to show you this one, for example. So let's say we've got a function, and we say there's a jump happening right there. So it's kind of moving along, and then there's this closed circle here, and then it jumps down to that open circle and continues on its way. So the question is, would this function be continuous at a? And just kind of using your intuition, you might say, no, that's not continuous. It has a jump, right? There's this break. And that's absolutely right. So, but exactly why? If we're looking at this definition with the limit equals f of a, what is that all about? So, if we were to look at each part, maybe I'll slide this up. You probably remember that the limit of the function as x approaches a here does not exist, because the left side is going to this y value, the right side is going to this other y value, and they're not equal. So the limit does not exist. Well, if the limit doesn't exist, then certainly the limit cannot equal anything else. And so we can stop right there and say, no, this is not continuous. We call it discontinuous. And we even give this type a particular name. We call it a jump discontinuity because, well, it's got the jump there. Okay, let's look at another one. There's another drawing. Let me slide this up. Okay, so our function is just kind of cruising along, but right there at a, it's got a missing point. We call that a hole. All right, so just that one point right there at a has been, think of it as just being like somebody plucked down and removed it and just kind of threw it away. There's that little gap there. Well, would this be continuous at a? Well, no, because even though it's infinitely small, there's still a little of a gap, right? Now, if you look at each part, in this case, the limit does exist, right? As we approach a from the left side and from the right side, because it's a hole, they are approaching the same y value from the left and the right. So it's not an issue of f of x being d and e this time. It does exist, but, well, it's the other one, right? So the function value at a does not exist. And for this to be continuous, these will have to equal. Well, we get an answer here because it's whatever that y value is, but if the function value doesn't exist, well, they certainly cannot be equal. So we give this a different type of name. We call this one a removable discontinuity. And, well, the word removable, because it's like somebody reached down and removed that one point and just kind of flicked it to the side. Okay, so that is not continuous, all right? Moving on. What if we did this? Very similar to the last drawing, but instead of removing that point completely, it's just been relocated. All right. So we've got our function cruising along. Everything seems fine, but right there at A, somebody took that point out. They picked it up and they just dropped it off a little bit higher up. If you thought about the different parts, well, hey, the limit does exist, right? But they're not equal. Okay, so the limit value would be down here, this y value. The function value, though, is up there. And now they both exist, finally, but they're not at the same location. They're not at the same y value. So that is discontinuous as well. We're still going to call this one removable. So both of these cases get the same name because it's like, again, somebody removed that point. Here they just happen to relocate it instead of tossing it away to the side or something. Okay. Turns out there's one more case for a discontinuity, and then we'll finally see something that is continuous. How about this? So I've drawn a vertical asymptote there. It's happening there at A. And the graph has, this sort of behavior, fairly typical around an asymptote. You think, well, is this function continuous at A? Well, of course not, right? The limit does not exist. Actually, both don't exist here. The limit doesn't exist because the left and the right sides are going to different places. And certainly f of a doesn't exist. It's undefined because that's where the asymptote occurs. So certainly this is not continuous. You can't have d and e equals d and e. That doesn't work. So what do we call this type? That is an infinite discontinuity. These two sides are infinitely far apart. I guess you could argue it's a jump, but it's like an infinitely far jump. And so we'll give that a new name. Okay, so the three types of discontinuities are the jump, the removable, and the infinite. So keep that in mind. Okay, finally, we're going to look at this one. Now you get a graph of something that's finally continuous. And so what's going on here? Well, you could say, well, nothing unusual is happening. So I've drawn the dot there at A, but I really wouldn't have to. I mean, this function is just moving through, it passes through A, and nothing special happens. There's no jump, there's no missing point, there's no vertical asymptote. Okay, it's just we call it a nice smooth curve there, nothing unusual, nothing out of the ordinary. So, and in this case, we see that the definition does finally hold. The limit of f of x as x approaches a does equal f of a. The limit comes in right there to that y value, and the function is at the same location. So that's finally continuous. Okay, and the way we might say that, I said it just a moment ago, the function is smooth, if you will, at x equals a. Okay, let's keep going. We'll get into some examples here. We're going to start with this. For example, state all x values where f of x is discontinuous, and then state intervals where f of x is continuous. Okay, well, let's see what we've got in store here. Number one, hey, this might look familiar. It's our graph. We saw this graph back at the beginning of 2.2, same exact graph. I recommend you copy this, just like I recommend you be writing all of this stuff down. So I've gone 5 in each direction, like so, and Well, maybe hit pause and copy that. Okay, so we want to state all of the x values where the function is discontinuous. Let's start with that. So you think, okay, well, these arrows indicate it's going on forever in both directions. So everything looks fine. You know, we pass through this point. No, you know, that's fine. That's fine. We pass through here, and you know, it's all linked. It's all smooth. Okay, there's actually kind of an edge there, but that's okay. Then we get to this location and we've got to jump. So there's definitely a discontinuity happening at 1. And then the function continues, and oh, we've got a hole there at 4. We call that removable, right? Okay, so I think we can say those are our 2 points where it's discontinuous. I think I'm just going to show you all of this. So our answer would be it's discontinuous at x equals 1, and I'll even note which type. Be prepared for that to identify which type of discontinuity. That's a jump discontinuity, and at x equals 4, a removable. So what does that mean for the second part? State the intervals where f of x is continuous. Well, it's continuous at every other point. Okay? Every other point, this works. So we'd say, all right, well, from negative infinity up to 1, all these values, it's continuous. Then we have to skip over 1, pick it up from 1 to 4, and then union 4 to infinity. And there you have it. Okay, let's stop this video here. We got more examples, more difficult examples to come in the next one.